In this presentation, we are going to discuss one example based on block diagram reduction. So, let's get started. Using block diagram reduction, find the transfer function of the system whose block diagram is shown in the below figure. One block diagram representation is given to us and we need to find out the overall transfer function by using the block diagram reduction rules. If we observe this block diagram representation, we are given two adders. There are three blocks having gains G1, G2 and G3. There is a negative feedback having gain H1 which is connected to this adder, and there is one more negative feedback having gain H2 which is connected to this adder. The reference input is R and the final output is C, and we need to find out the overall transfer function. I'll recommend you all to go through all the block diagram reduction rules before moving on to this example. So moving on to the solution, firstly we need to observe this block diagram representation and think from where we can start the problem. Block diagram reduction is a step-by-step approach in finding the overall transfer function. And if we pick the correct point at the very first step, then it makes the problem very simple. So observe this block diagram representation and think from where we can start the problem. Okay, so observe this takeoff point. If we shift this takeoff point after this block, then what will happen? Yes, if we shift this takeoff point after this block, then these two blocks will come in series and we can multiply the gains of these blocks. So our step number 1 is shifting of this takeoff point after this block. And if we shift this takeoff point after this block, then the block diagram representation will look like this. See, we have shifted this takeoff point after this block. And from the rule number 5 that we have discussed in the block diagram representation, we all know that we shift a takeoff point after a block, then we need to divide the gain of this block with the gain of this takeoff point. And the gain of this takeoff point in this case is H1. So if we divide the gain of this block with the gain of this takeoff point, we will have H1 over G3. Now what will be the next step? Yes, these two blocks are now in series, so we will multiply the gains of these two blocks. So moving on to step number 2, in which we will multiply the gains of these two blocks. So in step number 2, if we multiply the gains of blocks which are present in series, the block diagram representation will look like this, in which we have replaced the two blocks with a single block, and the gain of this block will be the product of individual gains of those two blocks. It will be equal to G2 multiplied with G3. Now observe the block diagram representation and think what can be the next step. Yes, if we observe this portion, we can see this is a negative feedback system and we can convert this into a single block if we calculate its overall closed loop transfer function. And we all know the closed loop transfer function for a negative feedback system is Gs over 1 plus GSHS, where Gs is the forward path gain, which is equal to G2 multiplied with G3 in our case, and Hs is the feedback path gain, which is equal to H2 in our case. So our step number 3 will be solving the negative feedback. And if we convert this negative feedback into a single block, then the block diagram representation will look like this. And the gain of this block will be the closed loop transfer function of this negative feedback. It will be G2 G3 over 1 plus G2 G3 H2. So the gain of this block will be G2 multiplied with G3 over 1 plus G2 G3 H2. Now we can clearly see that these two blocks are now in series and we can multiply the gains of these two blocks. If we multiply the gains of these two blocks, the overall gain will be G1 G2 G3 over 1 plus G2 G3 H2. And after that, if we observe this complete closed loop system, it is a negative feedback system. So we can solve this negative feedback system in order to calculate the overall transfer function. So our last step will be solving of this negative feedback system, in which the forward path gain will be G1 G2 G3 over 1 plus G2 G3 H2, and the feedback path gain is H1 over G3. So moving on to the step number 4, which is solving the negative feedback. And if we solve the negative feedback, we can replace the complete system with a single block. and the gain of this block will be the overall closed loop transfer function. So the gain of this block will be G1 G2 G3 over 1 plus G2 G3 H2 divided by 1 plus G1 G2 G3 over 1 plus G2 G3 H2 multiplied with H1 over G3. If we observe, this gain G1 G2 G3 over 1 plus G2 G3 H2 is the forward path gain of the negative feedback system, and H1 over G3 is the feedback path gain of the negative feedback system. And we have used the formula Gs over 1 plus GSHS in order to evaluate the negative feedback. Now we can see that this G3 in the denominator and this G3 in the numerator will get cancelled, and after that if we take the LCM, then this denominator term 1 plus G2 G3 H2 will get cancelled with this term 1 plus G2 G3 H2, and we will have the overall transfer function as G2 G3 H2 over 1 plus G2 G3 H2 plus G1 G2 H1. I hope you got this. So now the overall transfer function of the system is C over R equal to G2 G3 H2 over 1 plus G2 G3 H2 plus G1 G2 H1. This is the answer to the problem, and we have calculated this by the use of block diagram reduction rules. We will discuss some more examples based on block diagram reduction rules in the upcoming lectures. Thank you for watching this lecture. I'll end this one here. See you in the next lecture.